Here's the city of Atlanta proper, a mid sized American metropolis with many accessible attractions and events happening year round. But then here's Metro Atlanta, a conflicting system of loosely connected neighborhoods operating as their own separate microcommunities. These two networks contrast heavily, creating a strong sense of disconnect in Atlanta. In the large suburbia, people can feel trapped, driving 20 minutes in one direction just to get nowhere. While in the heart of the city, you can walk for half that time and pass a coffee shop, a local gym, and a park all in a single stretch. That trapped feeling, though, is far more than just a feeling. If you look at Atlanta just a little bit deeper, you can define that feeling using graphs. Places, like a cul-de-sac or an intersection, are nodes or points. Movement between those places, like a road or sidewalk, those are the edges, aka the lines. Atlanta is full of nodes, but what are nodes without meaningful edges? So let's take a look at Atlanta's nodes and edges and really lay a finger on that disconnected feeling. Welcome to Atlanta. To see why Atlanta feels so disconnected, we need some ideas from graph theory. As mentioned before, there are two core elements of graph theory: nodes, which are the places in Atlanta, and edges, which are the paths, like sidewalks and roads. To really analyze and understand Atlanta, we'll need a few more concepts: the degree of a place, the centrality of a path, and the components of a city. The degree of a place is simply how many ways there are to leave it. A cul-de-sac has a very low degree, while a major intersection has a high one. The centrality of a path is the measure of how often the path lies along the shortest route between two places. High centrality means many routes flow through that path, so it has a high usage. Components are part of the overall map where places are connected to each other but poorly connected to the rest of the map. Think of Atlanta's suburbs, which typically have a single way in and out. Now that we have the tools needed to describe a city, let's take a look at the city of Atlanta proper to see what true connection is like. For this portion of the video, we're going to focus on Midtown Atlanta, the city's artistic hub boasting the intellectually renowned Georgia Tech. Take a look at this map of Midtown. It looks like a typical city grid system, nothing special. But it's not about how it looks, it's about how it feels and functions. And I can say, with confidence, that this section of the city grid, along with the surrounding neighborhood, feels like a connected system. But how? What exactly makes it feel that way? That's exactly what graph theory is for, so let's turn this city grid into a simple graph. Before we get into any analysis, take note of the nodes around the perimeter of the 4x4. They all have edges attached to them that seem to lead to nowhere, but that's simply because this is just a section of the city, a smaller part of a larger grid. Omitting those lines would be disingenuous. Looking at our graph of the city, one thing immediately stands out: there are no disconnected subgraphs. If you take any block on the city grid, you realize that it's just as connected to the overall city grid as any other block is. This can easily be quantified using degrees and centrality. Take any node. We'll use this one for example. Notice how it has a degree of 4. There are 4 roads attached to this node. Now realize that every node has 4 roads. Every node has a degree of 4. Because there are 4 ways in and 4 ways out of every place, the city grid has redundancy. If this intersection shuts down, you can go a different way without a significant detour. And let's say, for some reason, you need to stop here before arriving at your final destination. You can easily loop it into your route. This incredible redundancy ties right back into centrality. Take these 2 points, point A and point B. What's the shortest route between them? Well, moving from node to node, you can get from A to B in 6 blocks using this route. But you can also use this route, or this one, or this one. I think you get the point. The diversity of routes means that no road bears a disproportionate amount of congestion. You might be thinking, why wouldn't everyone just go the shortest route from point A to point B? And you'd be right to think that, but remember, this is a model of real life. In the real world, people have shopping to do, kids to pick up, and other personal reasons as to why they'd take a different route. But most importantly, in real life, everyone is coming from different locations. No route is the route most taken because not everyone lives in the same place. Obviously, there are exceptions, like city attractions, events, and suburban to urban highways, but even under less than ideal conditions, this still holds true. So now that it's obvious why the city grid feels so connected, why don't suburbs feel the same way? Here's another map. Immediately, it tells a completely different story. It's so windy and twisty, so branchy, and that's deliberate word choice. This small neighborhood is what I'll call a tree-like structure. Trees in graph theory are defined as connected, directionless graphs with no loops. You might notice that this graph has 3 loops, but all 3 of those loops are essentially useless. You could drive around them, but you'd have no reason to, unless you were the mailman. That's why it's tree-like. But here's the thing about trees. They're cascading structures. Cascading structures aren't exactly known for being very interconnected. They're made to distribute information downward and outward. In this case, cars out of the neighborhood. That lack of interconnectedness becomes ever more apparent from a graphical perspective. Let's first look at the degrees of our suburban neighborhood. These are our nodes. Every place where a road intersects another is a node, and every place where a road ends is a node. Basically, every node is either a T-junction or a cul-de-sac. Take note of how there is only one 4-way intersection. The highest possible degree in this suburb, and many others, is 3, 4 on a technicality. The lowest is 1, and there are no 2s. Now let's make a value for quantitative comparison. We'll call it the choice index. It's simply the average number of degrees in a system. Our choice index for this suburb averages out to about 2.4. A city block, on the other hand, averages out to exactly 4. The choice index doesn't tell us the full story, though. Sample size is also important. While the suburb had a sample size of 18 nodes, the city block had a sample size of 16 nodes. And that's all considering the fact that the suburb is about 11 times the size of the city block. If we scaled the city block to match, it would boast 176 nodes. So in this city, you not only have more of a choice of direction on average, but you also have more opportunities to make a choice in the first place, making movement from place to place blissfully easy. Next up, centrality and connected components. For our sake, they go hand in hand. Because this suburb is so tree-like, everything must traverse this road to get in and out, no exceptions, but that presents a problem. I propose a question to you. What happens to transportation if something were to block up that road? To be quite frank, there is something that this suburb does right. It has 2 entrances and exits, but that still isn't enough. The tree-like structure of this neighborhood means the internal components are extremely vulnerable to accidents, regardless of the main entrances and exits. But there are, without a doubt, millions of suburbs, large and small, with only a single entrance and exit. A sizable sinkhole or a fallen tree could completely cease transportation for at least a day. So, in many other suburbs, the high traffic, integral roads are the only ones preventing the neighborhood from becoming disconnected. And it's not unlikely that a connected intersection will be blocked, therefore disconnecting the neighborhood from the road. Let's make another value. I call it the crisis index. It measures network resilience by quantifying the amount of nodes that must be blocked before a system becomes unusable. To calculate it, a random node will be blocked off, simulating a crash, fallen tree, construction, etc. This continues until there is a crisis. I'll define a crisis as any disconnected home or group of homes. Then, we'll tally up the amount of nodes blocked, run more simulations, and average the results, comparing the final value to a city block like we did with the degrees. I'll do a manual simulation on screen before diving into the results of the simulation. In this rough example, node 8 is removed from the neighborhood. It could be blocked off, under construction, it doesn't really matter. As we can see, everyone can still exit and enter the neighborhood. Everyone on the right has access to exit 13, and everyone on the left has access to exit 1. But then, node 16 goes down. Now this is cause for concern because look at these houses. They can't go anywhere because both intersections connected to their street are down. So in this iteration, it only takes 2 accidents to cause a crisis in the neighborhood. I simulated circumstances just like these 1,000 times, and the results reflect what our manual simulation just showed. The average number of accidents per trial is about 1.28, meaning that it barely takes more than one accident to cause a crisis in this neighborhood. All of the short, one accident iterations are caused by the blockage of a cul-de-sac, a very fickle point in a neighborhood due to its low degree. But when it comes to the city block, one accident isn't enough, and most of the time, two isn't either. The average accidents per trial in a city block is about 3.30, significantly higher than that of the neighborhood. If you'll notice, this value is extremely close to 3, meaning that in most trials, 3 accidents causes a crisis. Some will have 4 accidents and some will have 2, but 3 is a mathematical sweet spot. According to this information, the city grid, which is many times smaller than the suburban neighborhood, has a much higher capacity for accidents. This means that movement from place to place in the city is far less likely to be impeded than in a neighborhood. So, is that why Atlanta feels so disconnected? Partially, yes. There are a million reasons you could point to for why Atlanta functions the way it does, and there's no way I could hit every point in this video. But from what I did show in this video, it's easy to see that one of the main reasons Atlanta feels so disconnected is that Metro Atlanta is mostly suburbs. Suburban neighborhoods are inherently disconnected. Each little neighborhood is like its own microcommunity. And even within those neighborhoods, as the math shows, movement is limited, and sometimes it's completely checked out, creating a unique sense of disconnection. But honestly, the ultimate reason Atlanta feels so disconnected is that the suburbs and the city are just so different. The stark contrast between the vibrant, bustling city and the quiet, reserved suburbs is so exaggerated that they even have a saying for it. Atlanta is not Georgia.